Welcome. In this session, we'll begin exploring part 2 of the kernel trick for the support vector machine. Let's recall how scoring works. Let's recall that if we have labels yj which are either -1 or +1, that our rule is that we'll classify a vector as being in class -1 or class +1 using a hyperplane decision. So the hyperplane, using a hyperplane, what we do is we say that the score for data vector j is, and we can write this as, the way that we've been writing it is we'll take the transpose of the jth data vector times the weight vector that represents the hyperplane plus the bias scalar. And we could also write this as the dot product of the jth data vector and the weight vector plus the bias scalar. Now, let's consider the situation that we had in a previous lecture, which was, let's embed this jth data vector into a higher dimensional space. And the question is, how can we manage the weights? There's no guarantee that this embedding will preserve linearity, and it's not clear to us what linearity would be if we're embedding, for example, using a Gaussian function, because a Gaussian function requires computing an exponential, and an exponential is an infinite series. So we need some way to manage these weights. So let's recall the Lagrange equation, and this is the primal form. So the Lagrange function, and one Lagrange equation was that the weight vector could be represented as the transpose of the data vector times the label matrix times the Lagrange multipliers. And let's consider how we could use that to score our data. So our score would then become, the score of the jth data vector would then become, well, we could represent this as w dot j as well as x dot w. So let's transpose those. So let's say that we'll represent that as w transpose times the jth data vector plus the bias scalar. And now we can substitute this equation into this, so that has to equal, that would be x transpose y alpha transpose times the jth data vector plus the bias scalar. And we can then write that, as we work out that transpose, this would be alpha transpose, so the transpose of the Lagrange multipliers, times the label matrix, times the design matrix, times the jth data vector, plus the bias scalar. Let's explore this term in more detail. We can see that alpha transpose times y is going to be a diagonal matrix, and the entries of it will be alpha 1, so alpha transpose y will be, the first entry will be alpha 1 y1, and then the next diagonal entry will be alpha 2 y2, and so on until we get to alpha m ym. And now, what will x times xj be? What will the design matrix times xj be? Well, that x times xj will equal, so the first entry of that will be x1 transpose times xj. The second entry will be x2 transpose xj, and so on until we get to xm transpose xj. And we can combine this, and we can now represent this entire product as a sum. And that means that our score for the jth data vector will be, so when we take this times this, and then this entry times this, etc., that has to equal the sum as I goes from 1 to m of, this will be alpha I yi, so that's the ith entry here, and then the ith entry here is going to be xi dot xj, because xi transpose xj is xi dot xj plus the bias scalar. Now, this would be working with, this would be what we have if we don't embed the data. So now, let's consider embedded data. We won't actually use the embedded data, but let's consider it, is that we would replace this xi dot xj with x hat I dot x hat j. And that would require going through the embedding and the dot product, and that is equal to the kernel function applied to the original vectors. And that means that now we can consider the kernel function. And if we consider this kernel function, what we do is we replace this dot product with the kernel. And so the score of the jth data vector will now be, this will be the sum as I goes from 1 to m of alpha I yi, and now we'll use the kernel function of the ith data vector and the jth data vector that we're trying to score, and then we'll add b. Now, let's pull back and remember how Lagrange multipliers work. The Lagrange multiplier will be non-zero if the constraint is active, and it will be 0 if the constraint is inactive. Here, a Lagrange multiplier will be 0 if the data vector is not a support vector, and the alpha Lagrange multiplier will be strictly positive if it is a support vector. So we will write the set of indexes of support vectors as, let's write that as our blackboard n with an S subscript. We can then say that the score of the jth data vector, rather than going through all possible vectors, because we know that some of these, most of them, are going to be non-support vectors with alphas 0, we can make the computation much more effective by saying sum over all I that index support vectors times the Lagrange multiplier for the support vector times the label for the support vector times the kernel function of the support vector and the vector that we're trying to score, and then add the bias scalar. And then classify as the quantization of the jth vector will just be the sign function of the score. And this computation and this classification are how MATLAB, as we're currently using it, performs these, and we'll be, in some assignments, we'll be going through and we'll be performing this scoring ourselves and performing this classification ourselves.